Hello everyone. Welcome back to physics. Let me start with a curious thought. If steel is so strong, why does a skyscraper made of steel still sway slightly in the wind? Shouldn't it stand perfectly stiff like a frozen statue? Well, here's the surprise, no solid is perfectly rigid. Even something as tough as steel bends, stretches, or compresses when forces act on it. In our ideal world of rigid bodies, shape and size never change. But in reality, every solid resists deformation only up to a point. Push hard enough and it deforms. And this is why engineers lose sleep at night. They must know exactly how much a material bends or compresses before it breaks. From bridges to rockets, this is what keeps them safe and standing. As you can see in the diagram, the so-called rigid bar bends slightly when force is applied, a reminder that perfect rigidity is just a physics myth. Now let's move to the hero of today's discussion, elasticity. Imagine pulling a spring. You tug gently, the length increases a little. And once you let go, the spring bounces back to its original size as if saying, "Nice try, but you can't change me permanently." This ability of a solid to regain its shape and size when the applied force is removed is called elasticity. The temporary change during stretching is what we call elastic deformation. In fact, within certain limits, the extension of a spring is directly proportional to the applied force. Meaning extension depends linearly on the applied force as long as we stay within the elastic limit. Look at the diagram of the stretched helical spring. It stretches when pulled, but snaps right back when the force is removed. That's elasticity in action. Of course, not all materials are as disciplined as springs. Take putty or mud, you press it, and boom, it just flattens. No coming back. This is what we call plasticity. A plastic body undergoes permanent deformation. It doesn't have the elastic memory to return to its original shape. So unlike springs, putty doesn't whisper, "I'll be back." It simply stays squashed forever. In short, elasticity is reversible, plasticity is irreversible. The diagram here shows exactly that, a lump of putty squished between hands, permanently reshaped. So next time someone hands you a stress ball, remember, it's not just fun, it's material science at your fingertips. Now you might wonder, okay, this is cool, but why should I care about elasticity in real life? Well, without elastic properties, we wouldn't even have safe bridges or tall buildings. The entire safety of engineering structures depends on knowing exactly how materials respond to loads. Take steel, with its high elasticity, it's perfect for bridges. Glass, on the other hand, is brittle. Drop it, and it shatters. Brass, too soft for the job. Artificial limbs are another fascinating example. Engineers carefully select materials with the right elastic modulus so that the limb is both lightweight and strong enough to withstand walking or running. And the key formula here is Hooke's law in its general form: stress equals Young's modulus times strain. Where stress is sigma, strain is epsilon, and Young's modulus E is a constant that measures stiffness of the material. In short, elasticity isn't just a chapter in physics. It's what keeps aircraft wings from breaking midair and ropeways from snapping under load. So, let's wrap this up. Friction originates from the microscopic roughness of surfaces and the interlocking of their projections. It is self-adjusting. It increases with your push until it reaches a maximum, beyond which motion starts. The everyday examples of a car, a rolling ball, or a bicycle are proof of how friction silently governs motion around us. In mathematical form, the key takeaway is Maximum static friction equals mu sub S times N. Friction is not just a nuisance, it's the reason we can walk without slipping, write with a pen, or even drive cars safely. Imagine life without friction. We'd be sliding around endlessly like cartoon characters on ice. Alright, students, I hope this gives you a clear and fun picture of how friction originates. In our next session, we'll dive deeper into the laws of friction and see how this force behaves in motion. Until then, keep observing the little frictions of daily life, they're all part of physics in action.